the introduction to today's session. Okay, if there are no more comments, let me go now with the work for next sessions. Let me first remind you that we will not have a session next Friday, so June 5th, there will not be a session. So we'll have next session next June 12th. Okay, 12th of June will be next session. So you have 2 weeks to prepare the job for that session, which I'll next describe. We start with the new module, module 3. We finish with input-output, and we'll go now with the microarchitecture of the EH1 core, and we'll also analyze some other things outside EH1, which I'll describe later. Let's go into module 3, where the previous tasks are detailed. This is the work to complete between June 1st and June 11th. You have more time than usually because next session is June 12th. First task is to review a simple pipeline processor, 5 stages processor, such as the one studied in the typical books, Hennessy-Patterson or Harris and Harris. And well, this, as when we talked about the RISC-V architecture, I said that probably most of you don't need to review this because you're very familiar with it. And again, probably most of you don't need to review a simple processor, but in case you need to, you can use any of these books or also the materials from this course that we teach in our school and which are provided here, both in Spanish and in English. So these are quite detailed slides about the processor proposed in the Harris and Harris book, the pipeline processor, and you can review whatever you need to. Okay, it's quite basic. It's from a course that we teach in the first course of the computer science degree. But you may have forgotten some of these things, so you have the materials there in case you need it. After this, we recommend you to watch this new video. It's in Spanish and in English, but automatically translated to English, as always. And it describes the microarchitecture of the EH1 processor in high detail, so you will use this information for completing the proposed exercises. Let me go inside the slides that are described in the video. Again, as usual, I won't go in detail as the video does, because you have that information already in the video, but I'll review quickly some of these slides in order for you to have a first approximation to it. You then can go for the details in the video. So let me open those slides. These are this is the presentation of the EH1 microarchitecture. In this course, we're using the VIR course, and specifically the EH1 core, although the VIR family contains 3 cores, as we already mentioned several times: the EH1 on the left, the EH2 on the center, and the EL2 on the right. The EL2 is the smallest processor. It only has, it's a 4-stage pipeline processor. EH1 on the left is the core that we're using in the course. It's a 9-stage pipeline processor, which we'll describe next. And the EH2 is similar to the EH1, but it's multi-threading. It has the ability to execute 2 threads at the same time. Sorry. They all are mostly in order cores, although the EH1 and the EH2 have some out-of-order capabilities, but in general, they are considered in order cores. So as for the EH1 processor, it's a 32-bit RISC-V processor. It supports the base ISA plus the C and M extensions. C stands for compressed, and M stands for multiply and divide instructions. And it implements a lot of advanced microarchitectural features, such as, well, first of all, it's a 9-stage, it has a deep pipeline, 9 stages. We'll review it in detail next. It has 5 data paths, 2 for integer instructions, 1 for load store, 1 for multiplication, 1 for division, integer and division instructions. It's a superscalar core, meaning that it can execute 2 instructions per cycle, up to 2 instructions per cycle. It supports multi-cycle operations. It has many forwarding paths for dealing with data hazards. It has quite good branch predictor, which is the G-share branch predictor. Probably you're familiar with it, or at least you've heard of it. It has an instruction catch, but not a data catch. But it has both data and instruction scratch pad. Scratch pad is a special memory which is software managed. I don't know if you've studied this kind of memories. It's a low. It has a low latency, similar to the catch, but it's managed by software. Well, in case you need it, you also have some references for understanding what a scratch pad in general is, and to understand it in detail in the EH1 core. Also, it supports unaligned stores and loads, also non-blocking loads and divisions, and it has a feature called secondary ALU that we'll analyze in some of our exercises. So this will be the summary of features that the EH1 core supports. And then we go in detail in each of these features, and we try to understand the microarchitecture in detail. Well, I'll go through some of these slides. Let me go directly to the figure showing the microarchitecture in detail. This is a view of the 9 stages of the EH1 processor. We cannot see many of the details, but it's good for us to have a view of the whole processor in one picture. So we see 1, 2, 3, 4, 5, 6, 7, 8, and 9 stages of the processor called FC1 and FC2. These are the 2 fetch stages. Align, which is the alignment stage. We'll see what each stage does later. This is the decode stage. You already know what's the decode stage. These are the 3 execution stages for executing the instruction. And finally, these are the commit and write back stages that write the results into the register file. As I said, this cannot be seen in detail, but it's good for us to have a view of the whole pipeline. After this, we have 2 slides that show us the details of each stage in 2 different pictures. So the first one is for the front-end fetch and align stages. The second one is for the back end of the processor, which is from the decode stage to the write back stage. Okay? Any questions so far about the microarchitecture? Now I'm going to go in detail for each of these stages. Any questions so far? As I'm saying, the video goes in more detail than I'm explaining here. So it's very recommendable that you visualize the video maybe more than one time, and you stop in each part for understanding it correctly. So no questions? Okay. So let's look at the front end of the processor. The front end is responsible of providing the two instructions that the backend will have to execute every cycle. So it has to provide two instructions per cycle, ideally. We know that this is probably not the case in real workloads because there are many stalls for different reasons, catch misses or hazards or many other situations that will not allow to achieve the ideal throughput of two instructions per cycle. But this the front end is responsible of providing up to two instructions per cycle. How does it achieve that number of instructions? Well, it has first two stages that fetch the instructions from the available memories. And which are the available memories? As we said, there is an instruction catch, there is an instruction scratch pad that in some cases can provide the instructions. Sorry. And there is an external memory which, in case of a catch miss, will provide instructions. Okay, so the first two memories, the catch and the scratch pad, will have a latency of 1 and will allow us to maintain the two instructions per cycle, the ideal two instructions per cycle. In case there is a miss in the catch, there will be a higher latency that we need to pay for accessing the external memory, and which will be of several cycles. So in that case, we'll have to stall the processor, and we will not keep up with the ideal throughput of two instructions per cycle. Okay, so fetch is divided in two cycles because we first need to compute the address to access memory, and that is the first fetch stage. And in the second fetch stage, we have to perform the real memory access. In case there is a catch hit, we'll have the instructions in a single cycle. In case there's a catch miss or the instructions are not fetched from the scratch pad, we have to stall and pay several cycles to access external memory. Okay? So the instructions fetched from memory will be inserted in these three buffers that will provide the instructions to the next stages. So we'll have these buffers to store instructions that will be consumed by this next stage, which is called the aligner. Okay, so the aligner will receive the instructions from these buffers, and the memories will fill the instructions into these buffers. Okay, so the aligner is responsible of selecting two instructions per cycle from these three buffers. Okay, this is a black box for us. We don't go in detail, although if you're interested, you can, as always, you can access the Verilog module that implements the aligner, but it's not necessary for us. We just assume that this is a hardware that will select two instructions in these three buffers and will provide one instruction in way 0, another instruction in way 1. Way is the name that we give when we have a superscalar processor. We have, in this case, 2 ways, but we can have a higher superscalar capacity. For example, 4 instructions per cycle or 8 instructions per cycle. In this case, we have a 2-way superscalar processor, so we can provide 2 instructions per cycle. One in way 0, this signal, one in way 1, this other signal. Okay, note that in the name of the signal, which is the real name that we use in the Verilog code, there is a 0 for way 0 instruction and a 1 for the way 1 instruction. If everything went ideally, we'll have 2 instructions per cycle provided to the instruction registers. Okay, 2 instructions will be stored in the instructions registers per cycle, so that the backend will be able to execute 2 instructions per cycle, as it will happen in the ideal case. Okay, any question about the front end of the EH1 processor? I mean, there probably will be many questions that you still don't know the answer for them, and that will be answered once you view the video slowly and you understand the microarchitecture from the video and from the documentation. But for what I've explained, do you have any question? Yes, okay. Now, as I was saying, ideally, we'll have 2 instructions provided per cycle to the backend. So let's go with the backend. The backend is responsible of executing the instructions. So if you see here on the left part, on the top, there is this instruction registers block, which is the same that we had on the right of the previous figure. The instruction registers are filled by the aligner and are consumed by the decoder of the processor. So the decoder will extract 2 instructions per cycle from the instruction registers. The instruction register, you probably are familiar with this name. This is the register that holds the instruction, and that was also present in the in the basic processors that you studied in computer architecture or computer fundamentals, or whatever name you gave it in the course you did in the degree, that where a simple pipeline processor was explained. It also used this name of instruction register. It's the register in the processor that holds the instruction that we're executing. Okay, so we are executing these 2 instructions in this superscalar processor, and these 2 instructions are provided to the decoder. The decoder is responsible of 2 things: generating the control signals in this control unit that understands the RISC-V architecture and is able to provide the control signals that will need the instructions, that will need the processor to execute these instructions. So these control signals will be provided to the remaining stages that will use them to control the execution of the instructions. This is clear? So the decoder will generate the control signals for the 2 instructions every cycle, and it will also be responsible of obtaining the sources for the instructions from the register file. So the decoder stage is responsible of 2 things: generating the control signals and obtaining the operands for the instructions from the register file. This is clear? Any question? Okay. Now, once the operands are obtained for the two instructions that will execute, the decoder will also need to assign each of the two instructions to the data path that correspond to them. So imagine that we have an add instruction and a load instruction. The decoder will send the add instruction through the I0 pipe, which is the pipeline or the data path for arithmetic logic instructions, such as the add instruction, and it will send the load instruction through this data path, which is the load store pipe, and which is responsible of executing loads and stores in this processor. Okay, so if the decoder has an add instruction and a load instruction, the first one will go through the I0 pipe. The second one, the load, will go through the LS pipe. Okay, they will be assigned to these two pipelines or data paths. Right. Now, any other combination of instructions would be possible. So we could have, for example, an add instruction followed by a subtract instruction. In that case, the first instruction, the add instruction, would go through the I0 pipe. The second instruction, which is a sub instruction, which is an arithmetic instruction, will go through the I1 pipe because the processor allows two arithmetic logic instructions to travel in parallel. Okay? For example, another combination, multiplication and a store instruction. Well, in that case, the processor allows both instructions to go in parallel again. So there is the mult pipe for the multiplication and the load store pipe for the store. So the decoder would send the mult through the data path for the mult instructions, mult pipe, the orange or pink or whatever color this is for the mult instruction, and the green data path for the store instruction. Okay? Understood that part? Now, there are other combinations that are not allowed and that will require the second instruction to stall due to a structural hazard. So, for example, let's say that we have two multiplications in the program which are sequential, one after the other. In that case, the first multiplication will be able to continue execution, but the second one will have to stall in the decode stage because only one data path for multiplications is available. Okay, so that would be a structural hazard, and that is resolved by making the second multiplication stop and wait until the mult pipe is available for it. Is that clear? That is a structural hazard, and the second instruction has to wait for the multiplication unit or the mult pipe, as we call it in this figure, is available, is free. Okay. Now the multiplication pipe or the multiplication functional unit is pipelined. That means that we can have more than one multiplication as long as they are in different stages. So the first multiplication could progress to the second stage at the same time that the second multiplication progresses to the first stage. So we have one multiplication here, another multiplication here. That is possible. They cannot be in the same stage, but they can be in consecutive stages, in different stages, because the functional unit is pipelined. That is clear? Similarly, thank you, Harriet. Similarly, load store unit is pipeline. So we can have a load followed by another load. We cannot have them in parallel in the same stage at the same time, but we can have them back to back, meaning that we can have one in one stage and the other one in the previous stage. So in the case we have two loads, two consecutive loads, we'll have to make the second one stall in the code, but then in the next cycle it can start execution. Okay. Similarly, we can have data hazards. You probably all know what a data hazard is. In case you don't remember, you can go to the slides where the simple processor, simple 5-stage processor is explained. The different kinds of hazards are defined there and are explained with examples, and well, all that you need is there. So in case you need to, you can go to review these concepts there. Probably you don't need to review what a data hazard is. So in case of a data hazard, we may need to stall or we may use forwarding paths. Okay, so different forwarding paths are provided in the processor. So the decode stage will determine if a forwarding path can be used, and in that case it will use it, or if it has to make an instruction stall until the result is available. Let me give you an example of a data hazard with a stall required. So let's imagine that we have a multiplication that generates a result that the next instruction will use. And the next instruction is, for example, an add instruction. Okay, we have a multiplication followed by an add instruction. They both achieve the decode stage at the same time. But the multiplication will progress and the add will stall in the decode stage. Why is that? Because the add depends on the result of the multiplication. Once the multiplication obtains its results, and that happens in the third stage of execution, you can see that the multiplier extends for these 3 stages, meaning that the result is not available until the third stage. Now, once the result is available, it can be forwarded to the add instruction, which is waiting at the decode stage. So 2 cycles, two stages will have what is usually called a bubble, meaning that we're not doing work in these 2 cycles, and in the next cycle, the add instruction will receive the result from the multiplication. Do you understand that example? There will be some examples provided later that will allow you to understand these concepts. Okay, so if you don't have them clear, don't worry, you'll be able to practice with them later. Any question? Is this clear? Okay. From my side, this is it for the microarchitecture of the EH1 processor. There are many other things that are explained in the video, and I think it's better that you look at them in the video. You can stop whenever you need, whenever you don't understand anything, you can review it, and you can, as always, ask me through the email or through a tutorship or in the class whenever you need it. Okay, as I said, many other explanations are given in the presentation. You have them in the video. So please look at the video slowly, repeat whatever you need, and try to understand the whole microarchitecture of the EH1 on your own. Now, as for the tasks, it's to watch the video and then to perform some examples based on a simulator. Specifically, we'll perform two examples based on the RVFPGA pipeline simulator, which you should have already used in the initial lab of the RVFPGA familiarization. An example was given using the RVFPGA pipeline that you should have done. So 2 more examples are provided here that you have to replicate and understand. It will help you understand the simulator and also the EH1 microarchitecture. So please do them in your computer. Try to understand all these guided examples that will help you understand the microarchitecture. And then there is another example using the RVFPGA trace simulator, and that lets us understand how the add instruction is executed in the EH1 core. Okay, so please also replicate this example on your own so that you understand this basic instruction and how it is executed in the core. Okay, this is described in detail, both the execution in the simulator and the reason why this how this instruction is executed in the EH1 process. Okay, so these are the tasks that you should do before the next session, which will be on the 12th of July, of June, sorry, 12th of June, not next Friday, but the Friday in 2 weeks. And let me recap these tasks. So first of all, review a basic processor following these slides. Second, watch the video explaining the VIR EH1 microarchitecture in detail. Third, perform these 2 examples for the RVFPGA's pipeline simulator. And fourth, perform this guided example with the RVFPGA trace simulator, and that explains the add instruction in detail. Everything clear? Any question? Okay, no questions. Then if you do these tasks, you will be ready to complete the exercises included in the next session, which are only 2. One about the EH1 microarchitecture using the RVFPGA pipeline simulator. Another one also studying the EH1 microarchitecture, but using the RVFPGA trace simulator. As you see, in next session, we'll only need simulation, no board, and that's it. Okay, before finishing the presentation, I'd like to advance something else, which is related not with the next session, but with the 5th session. Next session will be 4th session. This is related with the 5th session. But I want to advance it because it's something that, in case you want to do, you will need to buy some hardware. So in order to have time enough, I want to tell you now. If I go into module 3B, which is the second part of module 3, and I go to the end of these explanations, there is one exercise, exercise 4, which will use other RISC-V cores. And specifically, if we go in this link, this is new for this year's micro-credential. We didn't do this last year. it's an interesting activity, but it's completely optional. Okay, and the main reason is that you need to buy some hardware on your own. So if you don't want to do it, you don't need to do it. You can get the best score in the micro credential, even though you don't do this. It's just for your interest in case you want to do it. And it uses a different core. It's not the VIR cores, but the Wally core. I don't know if you've heard of this Wally core. The Wally repo is provided here. It's a core supported by Open Hardware, which is quite new, and which will have a textbook in very next month in June. So as for the latest news, the book is going to be released next month. It explains in high detail this Wally core, and I think it's very, very interesting. It's been developed by David Harris and Sarah Harris, who are the authors of one of the books that we recommend. And it provides both an open core called Wally and a textbook which includes many, many details about this core. So the idea in this activity would be to run the core in the Nexus A7 board. Okay, the board that you have, the FPGA that you have, is one of the boards which is supported by this core. So all the instructions are provided here. No, not here, sorry, not in the Wally repo, but in the activity provided in the RVFPGA repo. And everything is guided here. And the only thing is that you need to buy a micro SD card and a micro SD card reader in case you want to do this activity. Okay, it's completely optional. Okay, so only if you're interested, you need to buy this hardware. I'm providing here 2 links where you can, from Amazon, where you can obtain the SD card and the SD card reader that you need. In case you have already an SD card and an SD card reader, you probably can use it, but we've only tested these 2 SD cards. So it may work or it may not work. So you'd have to test. The ones that have been tested by me are these 2 SD cards. Okay, and all the instructions are provided here. So if you perform this whole activity, you'll run the Wally core of the board, and you'll even run Linux, because as opposed to the VIR cores, the Wally core can run Linux. That makes it more interesting for that reason. Not only for that, but that is one reason that makes it a very interesting core. Okay, so the reason I'm explaining this is in case you will be interested in doing this activity, you can start looking for this hardware that you need to buy. The SD card that we recommend, or that has been tested, is around $20 or 20 euros, and the SD card reader is also around 20 euros. So it would be around 40 euros that you have to pay in case you want to do this activity. Okay, as I say, it's completely optional. My idea is to provide this hardware next year with the board, so that you don't need to buy it and you can all do the activity. For this year, that was not possible. So in case you're interested in doing this, I'm afraid you will have to buy the material. Okay. And that's it from my side. Any comments, any questions? One thing more. For those of you who come to the lab, I can lend you an SD card that we have available in case you're interested in doing this activity. So Christina and Daniel, who are the 2 persons who I think may come to the lab, you don't need to buy these materials. I would lend them to you in case you want to do it. Somebody's asking, Haris, can you share here the URL for the hardware, please? You can find on the GitHub. Okay, let me share with you the GitHub because it's important that you can find the GitHub. So instead of the hardware, I'll provide you. This is the GitHub. It's in module 3D, other RISC-V cores. And if you go down on this web, you'll see the required hardware. So here's the link to the SD card, the Kingston SD card that I've tested successfully. And here's the link to the SD card reader that I also tested. Is this enough, Haris? Have you found it? Yes, great. Any other question? Any other comment? By the way, these instructions, I think they are quite well tested, but as opposed to the other materials that have been tested by many persons, many students, many professors, this one is completely new and it's only been tested by me. So it could probably have some errors, which I'd be very grateful if you share them with me once you find them. I mean, if you buy this SD card reader, you shouldn't have problems. I've tested them on my own, but still, probably in the explanations, you will find some errors. So please share them with me so that I can correct them. Daniel, yes, you have the option to use it in the lab. Those of you who come to the lab will have the option to use it in the lab. Okay. Any other thing? Okay, so from my side, that's it. I'll be here till 2, but if you need to leave, you can leave now. I'll share this presentation with you through the GitHub as usual, and that's it. Please don't forget that next Friday, we don't have the session, so it will be June 12th, our next session. Okay, so thank you. Thank you. If you have any questions until 2, I'm here. Thank you.
Okay, thank you, Daniel. Bye-bye.
Yeah, thank you, Jordi.
Bye, have a nice weekend.
Bye-bye, Joseph. Same for you.